Okay, hello everyone. Our topic is New York City public transportation and shortest path algorithms. My name is Huiying Chen.
My name is Zifei Song.
And my name is Jiawei Tong.
My name is Yixin Wen.
Jiawei, let's start with the problem statement.
Yeah, so we all prefer the topic of shortest path problem is because it can be widely used in our daily life. And we chose to do research on New York City is because the public transportation is absolutely an important part of New York City. You know, almost everyone living in the city have to come into contact with urban facilities like subway and bus. So choosing the best and the fastest route will undoubtedly help people living more efficiently. So we finally came up with the following question. If we have the New York public transportation map and if we can compare different shortest path algorithm, in a different situation or scenarios, which algorithm is the optimal scheme and which factors affect the effectiveness of the algorithms? Well, the next part will be each team member's motivations. So I'll go first. I remember I visited New York City like 3 years ago, and I remember I was completely lost the moment I got off the JFK. But luckily we have Google Maps, so it can provide routes guidance for me. I know they have transit map on each station, but it just not shows as easy as fast as Google Map can. So my experience just motivated me to figure out how each route is calculated.
For me, I personally love traveling. I spent most of my vacation exploring different places and cultures. I can still remember the first time I visited New York City. I kind of lost myself facing the complicated public transportation. I was eager to know how the algorithms behind the maps like Google Map working. The topic to find the best solution for the path between two nodes in the model attracts me to understand the shortest path algorithms, and it is very meaningful for myself in reality.
My motivation is that public transportation in New York City is complicated. And as a New Yorker, I want to use the algorithm that we learn from the course to help people to navigate the transportation network and find optimal solutions to fit their needs.
For me, GPS applications are my most often used apps. So every time I travel around New York City with map applications, I found that different map applications may give different optimal passes, which make me curious about how different algorithms would affect the results.
So the subway data is available on the MTA's website. It's a massive and complicated transit system, as you can see. But if we use the mindset as this picture described on the left, the majority of the graph that can be created with this data is to create nodes for the stations, and stations that are directly connected will be linked by edges. So the underground network can be modeled as an undirected graph denoted by G equals to the side of V and E, where V representing the side of vertices and E representing the set of edges. One thing have to be mentioned here is in reality, we know that New York City subway sometimes may be delay and skip stations. But because that part of data is hard to define and hard to find, so it won't be taken into our considerations for now. We'll only include solid data. Next slide. Yeah. So based on the idea I just discussed, we can have the subway data to be organized like this. So each station will have a number to identify itself. Like the first station of line 1, the 242 Street. Each stop will also have its longitude and altitude recorded. for the calculation purpose. And the routes are just which station belongs to which subway lines. And we record that by recording the corresponding color of that lines and record it as the hex format of the color. And age is just marked as the connection between two stations.
For bus system in New York City, it has in total 327 bus routes in the 5 boroughs. We are able to find GTFS feed for the bus system on MTA's website. Again, each bus stop is considered as vertices of the graph, and each route is considered as edge of 2 vertices. We took geographic coordinate information for each stop and connected each stop along with the routes. Next page, please. There are additional information that we need to take into the consideration. The first one is the fare. Fare for subways and all buses except for the express bus is $2.75 per rider, and fare for express bus is $6.75 per riders. And the second one is the distance. Since we have the geographic coordinates information for bus stops and subway stations, we'll be able to use the Heathersing formula, which provided below to calculate the distance between 2 bus stops or subway stations. And the third one is the average time to travel from one station to another. We can calculate the average time by subtracting the departure time of a stop from arrival time to the next stop. And we sum them up, then we divide by the total number of the stops. And the last one is the possible wait time. In GTFS feed, the arrival time of the station is the same as its departure time. So we believe that is because the riders act differently when they got on or got off the transportations. Therefore, there's no particular wait time at each station. And in our algorithm, we will use 2 minutes as the wait time at each station.
And then I'm going to talk about the algorithms engaged in our project. And we picked 3 algorithms. The first one is Dijkstra algorithms, and the second one is BFS, and the third one is Floyd. And for Dijkstra algorithms, in terms to modeling, we regard each fork in the road as a vertex and the road between the fork and fork as an edge. And after we ran the algorithms, we found there are some disadvantages. Like if we think of the huge map of New York City, there are too many forks and roads, which means in the graph, there are too many vertices and edges. The Dijkstra algorithms, it has a better runtime complexity, like compared to Floyd, but it takes too much space if the graph is huge. And we come up to a solution that we append a block that directly covers the start point and end point. And we only run the algorithms inside the block, which means we don't need to run the algorithms on the entire map, which will reduce the data capacity. And for BFS, we found the best case for BFS is to find the route with the least traffic lights. And the reason is that in this case, we don't need to consider the weight of the edges, which means the graph becomes to a weighted graph. And the BFS give us the best time complexity of O of V plus E. Next page. And about the Floyd algorithms, we all know that it has a higher time complexity compared to others, and it's not suitable for computing the large amount of data. And by observing the map of New York City, we found out compared to the non-transfer stations, there are much more fewer transfer stations, which we think is a good case to use the Floyd algorithms. And we make the graph like the picture, where S0 refers to the start point, S1 and S2 refers to the transfer stations, and S3 refers to the endpoint. And we only ran the algorithms on between the S1 and S2. After we find the shortest path between S1 and S2, we connect the path with S0 and S3.
Beyond the algorithms that Zifi just mentioned, we also did some improvement regarding introduced parallel computing to Dijkstra algorithms. To solve large-scale and complex civil engineering problems, significant computing resources are required. In general, there are two computing approaches for solving such a problem. The first one is serial computing, and the second one is parallel computing. As we can see from the pseudo code of Dijkstra algorithm first generation, for this algorithm, the SD matrix was identical to the Freud algorithm. For convenience, the SP matrix was stored as a structure containing the starting and ending indexes of the each link in the shortest path of the given source. And the computational complexity of the pair's shortest path Dijkstra algorithm as big O of n cubed, where n represents the number of vertices. And in this implementation, noted as Dijkstra second model, the input distance metric A was decomposed by using a striped row-wise decomposition, and each processor only contained a portion of the distance matrix, and all other aspects of the implementation were identical to the previous one. Each processor was responsible for finding the shortest path for the sources corresponding to their assigned rows, and each processor generated portion of SD and SP metrics for these rows. The pseudocode for this implementation is as shown here. And as for the conclusion, all in all, finding the optimal route in a transportation network has been an important subject in such a transportation network analysis. In this final report, we research and compare the different algorithms to optimize the shortest or quickest path from start point A to destination B in a complexity of public transportation in New York City, including Dijkstra, BFS, and Freud algorithm. And we dive deep to optimize Dijkstra algorithm by introducing parallel computing, as parallel efficiency can be defined as a ratio of the runtime of a parallel algorithm to the runtime of the serial algorithm. The goal of the final report has been reached by employing functional and domain decomposition techniques. We believe that the performance of the algorithm could somewhat be helpful to release the heavy load of the large-scale public transportation problem in metropolitan cities such as New York. And thanks for listening.